Welcome you all. Today we discuss a very important topic, and this is known as time response. So we are moving towards basic concepts and analysis, what we can do, and then discuss how we do the control design. So first of all, look at what are the time response. So before discussing time response, we have to discuss what are poles, zeros, and then system response. Okay, what is pole? What is poles? Poles actually poles of a transfer function actually roots of the denominator. Similarly, what is poles? Zeros. So zeros are the roots of the denominator of the transfer functions. Okay. So if we have a transfer function, if we calculate the pole 0, so let's do an example. So we consider an example of first order system. How we define a system is first order. So order of the system is defined by number of poles in the system. So order is basically deal with the number of poles of the system. So if you have one pole, so this means that you have a first order system. Now for this example, what we have a system here with g of s given to us as s plus 2 divided by s plus 5. So we have some input to the system and some output to the system. So we can say that output is c of s and input is actually r of s. Okay, so this is a first order system because we have only single pole in it. Okay, and we assume that we are giving a step input to the system, and we just look at the Laplace of step is 1 by s. Okay, now when we have to look at the response, so we have to write, if I write the transfer function here, s plus 2 divided by s plus 5. Now first thing, how many poles we have? So we have only 1 0 and 1 pole. What is the location of poles? So first of all, poles that we have to put denominator equal to 0. From here we calculate the location of pole. So first location of pole is -2. Similarly for zeros, we have to put numerator equal to 0. For poles we have to put denominator equal to 0. For zeros we have to put numerator equal to 0. For in that case, sorry, I did a mistake here. This is not this is 5. Sorry about that. This is 5. Similarly for 0 we have to put numerator equal to 0, that is this, and this implies that s equal to -2. So there's only one pole and one 0 in the system. Now as we know that g of s actually equals to C of s divided by R of s, that is equal to s plus 2 divided by s plus 5. Now if we want to look at the response to this system, so response is basically the output of the system. Now output is denoted by C of s, so from this we just multiply with the, so we get R2 divided by s plus 5 times R of s. So as we know that R of s is a step input with a unit magnitude, so it becomes s times s plus 5. So this is what we are having here. Now so we discuss what is the pole, what is zeros, then we consider first order system. Now for first order system, so we can represent this first order system using a Laplace plane. So this is known as Laplace plane, S-plane, sometimes we call it S-plane, where you have a real part and you have an imaginary part on this axis. So now if I want to plot the poles, normally for poles we normally put cross, and for zeros we put circle. Now from here we can plot, so normally we represent cross for poles and circle for zeros. Now from here location for pole is -5, so assume that put cross here at -5. Similarly for pole 0 is -2, I put circle with -2. So this is the way we can represent on S-plane. Now we are interested in the response. So from response, this is the equation we getting. So as we know that from inverse Laplace transform, because we have to calculate in time domain, so if you remember you have to perform the partial fraction. So we have s plus 2 divided by s into s plus 5. Now you can have to do partial fraction at like this, if you remember. So if you calculate the partial fraction that come out, you can easily do it as for a is equal to, put s equal to 0, this becomes if you calculate it becomes 2 by 5. Similarly for b, you have to put s plus 5 times c of s and put s equal to -5, and you just plug in the values and it becomes 3 by 5. If anybody didn't understand how you get this thing, so it's very easy. You can go to my previous video on Laplace transform and Laplace overview. You can know how we calculate it. So from there we have s of s equal to 2 by 5 divided by s plus 3 by 5 divided by s plus 5. Now where I use Laplace table, now if I use the Laplace table, c of t become 2 by 5 plus, if I use for this 3 by 5 times exponential minus 5t. So this is the response we are getting for this first order system. Now if you look at, if I move further, so if you look at there are two parts of this one. So here when I do the partial fraction, so I have two parts. One is 2 by 5 divided by s, and other part is 3 by 5 divided by s plus 5. Okay. Now if I plot for system, if you remember, I plotted that pole is -5 and 0 is -2. So this actually, if I use a different color here, this one, okay, you to use different color. So this one is correspond to this pole. Similarly, if I use and these two, this one is the denominator that we are getting is basically due to the 0. So these numbers tell us how much add-in we need for these poles. Okay, and this one or that one, if I do here, this is the pole, this is due to the input of the system. Okay, so let me back to my pen. Okay, now if I look at the response when I apply the inverse Laplace transform, so I get so this part is known as force response because this is due to the input of the system, and this part is known as natural response. Okay. Natural response of the system. Now a pole of the input function generates the form of force response, that is the pole that at the origin generates a step at the output. So a pole at the transfer function generated the form of natural response is the pole at -5. So this is the basic idea that we get here from the response. So let me draw this response, how this response look like. So for example, this is time, okay, and we assume we start from 0 and so on. Okay. Now if I just plot the C of t, so 5/2 is a DC input actually, and when I plus with 3/5, so this means that when t equal to 0, so what we have okay, at 0, what is the value of this response? It's very easy to calculate. Just plug in the values. So you have 2/5 plus 3/5 at -5 times 0. So 0 is 1, so it becomes 1. Okay, right? Now when you increase the t, it start decaying. Okay, when it is infinity, so it will, what you say, so this is start from 1. Okay, what about infinity? 2.5 plus 3/5, when t tends to infinity it becomes minus infinity, so you know that this part becomes 0, so it will start from 1 and end at 2.5. so for example 2.5, for example this is 1, and assume that this is 2.5. so at 0 it will start from 1 and try to reach this one, that is 2.5. so this is the response you are getting for this system. Now if I make a journal, if I look at first order system in detail, how system response look like. So basically we divide response into two types. First is known as first order system response, and other is known as second order system response. So first order system response, normally we do have a transfer function, something like this. We give we have a transfer function of first order, we have an input which is R of s, we have an output which is C of s. This is our G of s, that is our plant. Okay, now let's see how this transfer function look like. Now for response, so we can write it G of s equal to C of s divided by R of s, which is equal A divided by s plus A. Now to find the C of s, we have to multiply by R of s times A divided by s plus A. Now the standard input that we use to check the response is known as step input. Okay, so for step input R of s, equal to step input, that is in Laplace is 1 over s. So C of s becomes a divided by s into s plus a. So this is what we get. When we apply the inverse Laplace, and we can write apply inverse Laplace C of t, it becomes 1 minus exponential minus at. So it has two parts. One is force response plus you have a natural response of the system. Okay. Now we defined some points here for this type of response. First one is known as time constant. Now for time constant is defined that we say that when your system reaches 63% of the final value, we call it as a time constant. Okay, so time constant is calculated when your system response reaches 63% of the final value. So for t equal to, so this means that if we put for 63% of final time, so in this case if we look at the natural response, that is C of t is equal to exponential minus at. Okay, now and the final force response, which is equal to 1 here. Okay, so this means that final value is 1, and if I take the 63% final value is equal to 63. So we have to calculate the time for which so we have to find t, so that c c of infinity goes to 63% of c final. So this is the basic idea that we can so we already discussed final value theorem. So from final value theorem, if you remember, you want limit t tends to infinity c of t, that gives you, if that is equal to limit when t tends to s tends to 0, Laplace s time c of s. So from here, if we plug in the values, we calculate the final value here. Okay, so this is the final value theorem. Okay, now for our current system, if we apply this, so we can say that t tends to infinity c of t, so it becomes s times limit when s tends to 0, s times a divided by s into s plus a. You cancel out this and put the limit, this becomes 1. Okay, so as we already know that 1 is the final value. Now to calculate the value that we get the 63%, so this implies that you have to use c of t, that is 1 minus exponential minus at for time constant. To calculate the time constant t, you have to find that this magnitude must be equal to 0.63, that is equal to 1 minus exponential minus at. Now the idea is to calculate t for what is t in this case. So how you do it, it's very easy. If I rewrite on next page, so the idea is minus 80 is equal to 0.63. So if I do a little manipulation, this means that 80 is equal to 0.37. Okay, just take this on the other side and we solve it. Now for this 0.37, it is only possible when your t is equal to 1 over a. So from here we calculate the time where we get the 63% of the final value, and this time is known as time constant. So now if I go to back and look at my transfer function, that was Cs divided by R of s, that is equal to A divided by S plus A. Look here, what is the location of pole? Pole is at S equal to minus A. So this means that time constant, normally we call it time constant for first order system only. Okay, remember this is true for first order system. We normally represent by tau, and which is equal to 1 over magnitude of the location of the A. So this is the time where you get 63% of the system response. So this is the time constant. If I do next and draw the response of 1 minus exponential minus at, okay, so responses look like something like this. Okay, if this is year 1, let me redraw it. I didn't draw it very well. Start from 0 and try to reach 1. So this is C of t. So this is year 0. So if we say this is the 63%, or we can say that this is equal to 0.63. So at this, the time is 1 over e. This is your time cost. So this is the representation we are getting for first order system only. Okay. Now the one thing that we have in first order system is known as time constant, and the second thing that we do have is known as rise time. We represented it by TR. So rise time is the time that took defined as the time for the response to reach from 10% to 90% of the final value. So 10 to percent. So this means that T rise is actually means that you are reaching between 10%, time reaching between 10%. That is nearly equal to 2.31 divided by A minus 0.11 divided by A, that is actually equal to 2.2 divided by A. So this is the time that you can reach the you have the rise time for the first order system. So in other words, if I draw it, it would start from here and try to reach 1. So if this is year 1, so if this is 10%, and if this is something like 90%, so the time in between this is known as rise time. Okay, So this is becomes 1 divided by a, and this becomes 231 divided by a. So this is the time, and the time is actually equal to 2.2 divided by a. So this is the time, and a is actually the pole of the system, location of the pole of the system. And third one, which we have in case of first order, is known as settling time, and we call it ts. Now settling time is equal to 4 divided by a, and is defined as the time for the response to reach and stay within 2% of its final value. So this time is known as settling time. So there are three properties in first order. One is known as time constant, second is rise time, and third is settling time. So if I draw a full picture, so let me redraw it. Okay, so okay, so it will start from here, try to reach 1 if this is 1, and we say that if this is the 10%, that is 0.1, and something here, this is 90%, 0.9, so this time is known as rise time. This time is known as the time between these two, rise time. And then we discuss if we reach something here around 0.63 value, and at this time, so here this time is known as, from 0 to this is known as time constant, that is equal to 1 over a if g of s is a divided by s plus a, which is first order system. Now the last thing we discuss is the settling time, and we say that if you reach 2%, 2% is around something here. After this sum, if it is within 2%, when you reach within 2%, that time is known as settling time. And it will also start from the 0. So this is the whole response to the system for step input. So this is first order response, and it has three properties. Remember that first one is time constant, that is denoted by tau, and tau is equal to 1 over magnitude of a for this particular transfer function, which has a on the top as well. Okay. Similarly, then the rise time, and we say that rise time is 2 divided by a, and third is the settling time, and we say that this is equal to 4 divided by a. So this is the property of the first order system. There is no overshoot, nothing like that. Okay. So I will stop here. We will continue further in next lecture.